Hello everyone, welcome to the extractive distillation simulation tutorial 2. As you know, in the previous tutorial, we have discussed the simulation of extractive distillation column. In this tutorial, we have discussed the recovery of solvent that we have used in the extractive distillation column. So here we have used phenol as the as a solvent in the extractive distillation column. So we need gonna learn the process or the simulation of distillation column that gonna separate phenol plus toluene in this extractive distillation process. So here, if you remember, this is our second objective of the simulation to learn the solvent recovery in the process, and also our we know the process parameter also says solvent recovery column has a number of stages and this is the estimate. So till now we have simulated the extractive distillation column. Now we have a in hand the mixture of phenol and toluene that is the bottom product that we gonna separate, and toluene come as the top product and phenol will be a bottom product. This thing you need to be remembered, and if you don't watch the previous lecture then go and watch. I have posted a link at the top, you can click from there and go and watch this. So let's go to the simulation now. Now what you need to do, you directly go there, open DWSIM. Once you open the DWSIM, maximize the window. Here you see open file. Go to the open file. I have saved the previous file as a extractive distillation one. I will click on this as open. It will open that simulation file with all the result calculated for me, so that I don't need to do the extractive distillation simulation again and again. Wait for a few seconds. DWSIM will load that file. Now the file is loaded. You can see I have the molar fraction of isooctane 0.99 as a top product. So this is the pure stream, but here I have a molar fraction of 0.71 and 0.28 for toluene or phenol. So bottom product is a mixed stream. We need to separate it. So as usual separations, we will first start with the shortcut distillation column to figure out the process parameters. Now for some time being, I will gonna click on this. What this will do, this will not allow the flowsheet calculate automatically, hence give me more time to do changes, and they are not directly going to simulate because simulation takes time and energy. Now go here. Here in the shortcut distillation column parameters, you will find light key component. So our light key component will be toluene because it is coming at the top. Heavy key will be phenol, and I want heavy key mole fraction in distillate less than 0.01. I will click on enter. Now what I will do, I have a condenser that is a total condenser, and I don't want any pressure drop, so I will choose same pressure drop. The height we don't need to play with this. We will do when you are gonna design the mechanical part of a distillation column also. That we will learn in some other simulation. So now click on the solve. Now this will calculate the whole flow sheet. Now just wait for a few seconds. This flow sheet will be calculated. So in 9.5 seconds, we can see here the flow sheet was calculated, 0 warning, 0 error. Here, as usual, the shortcut distillation column gives us the process parameter, minimum reflux ratio, which is 0.269. This is the main first intent of the shortcut distillation column. What I will do, as a rule of thumb, I will multiply 1.5 to the minimum reflux ratio to find out the reflux ratio that we are going to operate our column. So it will be 0.4. To make it more realistic, I will make it as a 0.41 or 0.4. Now what I will do, I am going to again simulate this to know the column parameters at the reflux ratio of 0.45. So you see minimum reflux ratio is not going to change because it is a mixture property and derived directly from the McApsel diagram. Now here the minimum number of stages doesn't also going to change, but the actual number of stages is 10.2, which means 11. So our estimate for the solvent recovery column, which we say has a number of stages 10, is wrong, and it will be gonna 11. And the optimal feed stage will be 4. And for that reflux ratio of 0.45, we have the revolvability of 7.61 kilowatt. We need to remember these parameters because they are gonna use in the ChemSep column. Now what you will do, you will just simply delete these all columns. Now what next we need to do, we need to stop the simulation, automatic simulations. Now I will drag and drop the ChemSep column. It is loaded. It has 11 states. Click on OK. Simple distillation, 11 states. They are going to open ChemSep column. Now you need to expose the energy ports. Click on save. Close this. Now here you can see feed stage. So it will be the bottom product. Correct. Outlet. Outlet. I am gonna generate energy also. Condenser duty need to be generated. Revolver duty need to be generated. Now let's rename this column. This column will be solvent. This will be the name of this column. Now this is my pure toluene. I will name it as a toluene TOLUENE product, and this as a phenol solvent. Why I am naming this? Because I already use phenol in the streams and I just want to give two different streams, two different names. Now E3 is my solvent recovery column, condenser duty, and E4 is the solvent recovery column, boiler duty. Now we have named all the streams for our convenience. Now I will click on this. I will say open cap open object editor. Now that editor will open. Here I will decheck this cap open properties. Then I will go to properties. Here it is asking me to predict the K values. I will go to use gamma phi, equation of state, Solvic SRK that I am gonna Solvic RK that I am gonna use. Now activity coefficient will be of unique vapor pressure, extended anatomy, enthalpy will be the excess enthalpy. Now next I will click on next. Here I don't want to make any change, no change till now. I also want to make a change in operation because we know the optimum feed stage is the fourth stage. Now I will go to the column specs. Here I see reflux ratio. We know the reflux ratio is 0.45, and the bottom specification we are gonna use the heat duty of revolver that we know 7.61 kilowatt, which will be converted as 7610 joule per second because here the parameter is in joule per second. Now what I will do, I will now run this. I will click on done. Now you see the mole fraction of toluene in the top product is 0.94, but I want it close to the 0.99. So what will I do now? I will see the McAfee graph. Here I see why it is not reached here. This point you see the mole fraction of toluene plus phenol. The mole fraction of toluene plus phenol. So here I have the pure toluene. Here I have the pure toluene in vapor phase. So you see I have not reached much there because this feed is here. If I move my feed stage to there, I have more probability to moving upward, or also if I increase the reflux ratio, this point is gonna come little lower and this graph gonna be steep. So first I am gonna change my reflux ratio. I am gonna make it as a 1, and then I just double it to check what happens when we double it. You see it become 0.9667. Now I will go to the operations. I will make it as a 6. I will bring it in the middle. Now I will see what happens. So you see here, you get 0.983158. Okay. So now I see there is an enrichment of the toluene that is happening. Now you see mecapthil. Now it is saying yes. There is a problem here. It is going till here. But what now more you can do, if you bring back your feed stage little bit there, 6 means like to make it 5. Let's see what happens. I make it not 5. I make it at 4. No, sorry. I make it at 7. I want to move it below. Then I click on run. It becomes 0.986, which is pretty much close to 0.99. So I will click on save. And then what I will do, I will close it. I remove this auto solve and gonna solve this. Now you will see this simulation might take a time, but yes, okay. It always says there is some error. Understandable. Got it. Energy port. Need to choose at a SRR duty. And again solve it because I want to know the duty also. Okay, not an issue. Outlet, everything is okay. Open the Capton operator. Units is valid. Why the results are not calculated? Okay. Yes, now I realize why this happens. I will go to column specs. As I connected this stream, as it is a 00 stream, take it as a 00, where the initial gas for us it was revolver duty 7. Now you see, I am gonna run it now. So now the previous parameter gonna return. I will click this one, then I will say solve. Sometimes this happens and this is how you learn basically. Okay, not an issue. What I will do, go to this energy stream. Solvent recovery should be the not inlet. Okay, energy flow 7610. I am gonna claim it as a 7610 and I will say please. Okay, this is the issue. This is the issue. This is too much. We know it is 7.6 kilowatt. Okay, that's it. Let me delete this energy stream first so that I may know what kind of error has occurred. I need to click on I should not delete that stream basically. What I need to do, I need to bring the energy stream. That will serve me the purpose till the time this error is going. This is annoying to me also. I will what I will do, I will solve it now. I don't want any error. Yes. Now I will connect. Okay, so it is a E4, not a issue. I will go to the capstone operator. This issue happens because of some things that I know. Column specs again become as 07610. I need to save, run. Done. Save. Got it. Now it will be solved. Definitely, I believe this is gonna be solved. Yeah, I don't know why for some reasons the it is not gonna take this 7610. I'm gonna say, and then I gonna say run. Now I will say click on save. Now I will gonna solve this. Till the time 7610 not gonna solve, we are not gonna get it our work done. Yes, it is solved. Now I just need to connect, or I might disconnect for the sake of being. This time we know because I assume the solvent. Why this happens? Because I already assumed the condenser reboiler duty, so I don't. This is not gonna be output parameter of simulation. This is a input parameter of the simulation. So that's why whenever I am attaching energy stream, the input is going as 0 and then everything goes blow up. So now what I will do, I will now use the analysis tool that is sorry, this stops for some function, but the next video what we are going to discuss, we are going to discuss about next to connect this recycled stream, the recycled stream of phenol back to this column, that will using a recycle block, and that is going to be a very useful simulation, so that we are going to in the next video.